Experiment 7. We kind of stopped lecture right at sort of these topics, or the completed topics, I guess, of this experiment. But I'm going to introduce it to you, and so we're going to talk about sort of what's going on in this experiment, in case you obviously want to get started on it, since it is the end of the week here. And obviously, next week we definitely will get into more detail about some of the calculations you may need to do on some of the pre-lab questions, post-lab questions, and maybe the experiment itself. But we will sort of talk about it. We'll talk about when it will be due and sort of what type of experiment, all that, as we go through it. So this is experiment 7 here, I believe. And this is the chemical formula of silver chloride and tin oxide. So chemical formula of silver chloride and tin oxide. All right. So there's kind of two parts to this experiment, part 1 and part 2. So I guess the kind of good news right off the bat is there's going to be probably no part 2. So that's the good news, I suppose. So really just part 1 of this experiment is pretty much all we're going to do, because I believe that is sort of all they filmed when they were doing these. So we will be doing just part 1 of this experiment. It is a formal experiment. So like the hydrate experiment, again, this is another one of the sort of formal experiments. So just up front, like we did with that hydrate experiment, you are supposed to be using your carbon pages in the back of your lab manual. Again, you're really only supposed to be using sort of the procedure and the data tables that you see in the actual experiment as sort of guides to what you should be writing in your sort of lab notebook, your carbon pages. So remember that when you're doing these experiments, technically you're not supposed to be filling in the kind of pre-made for you tables and stuff like that that you see in the actual manual, but you should be recreating those, as we talked about with the hydrate experiment, in your carbon pages. You obviously should have it set up like we talked about last experiment as well, with the procedure there. And again, you do need to write the procedure as if you were performing the experiment. So again, here it would just be part 1, as there's no part 2 to this experiment that we'll be doing. And you also need to obviously have a space for observations, where you can take observations, as in your case, when you're watching the video, again, of things that, maybe change color, color changes, precipitations made, so some of those sort of qualitative observations you should be making in your carbon pages, along with, obviously, most everybody will probably recreate the table that you find in the manual in your carbon pages. You should be filling in the data information as well, numbers, values, and those type of things. So again, another formal sort of experiment. The use of the carbon pages should be done, just like what we did with the hydrate experiment. The only things technically that you can write on from the actual manual itself is the pre and post lab questions. So again, you can't just answer those questions directly on those papers, but again, the procedure, the observations, the data table, sample calculations, again, those should be put into the carbon pages in your notebook. And again, this will also then require you to write up or type up a type report for this experiment as well. So sort of the report and the way that you should do this experiment is very similar to, obviously, I think it was the actual last experiment we did there, which was experiment 6, the hydrate experiment, again, and that formal aspect of it. Any questions on sort of that there? Now, let's talk a little bit about this experiment and some of the calculations that you will be doing in this experiment and sort of what's happening in this experiment. Some of these calculations, again, we haven't really got to. It is pretty much kind of where we laid up there in lecture, but I'm just going to kind of preview sort of some of those calculations, and then we will get to it for sure on Tuesday's lecture, and you'll obviously have that. So a couple of things of importance is we're trying to find a chemical formula, right? And when we're trying to find a chemical formula, something like H2O is a chemical formula, right? Within a chemical formula, we have subscripts, right? And those subscripts basically tell us how many atoms of each of the elements that we have. The subscripts always go to the guy to the left of it. And again, if nothing is written there, it's assumed to be one of those things. Now, in addition, those subscripts that we see do represent the moles of each of those guys. They actually represent the moles of hydrogen in this case, and actually the moles of oxygen that are there as well. So we talked a little bit about moles today, obviously. So really the goal of this sort of experiment is we're going to try to figure out what is the actual formula for silver chloride through an experimental sort of process. Now, a couple of things when we talk about formulas, there's really two types of formulas. And like I said, it's sort of where we left off in lecture. And again, we'll pick it up on Tuesday for sure. But there's two types of formulas. One is what is known as the empirical formula. And one is known as the molecular formula. The empirical formula is really the simplest whole number ratio of what is present. The molecular formula tells us exactly what is present in terms of the elements. Exactly how many hydrogens there are, how many oxygens there are. So, if we take something like C2H4, for example, this could be its molecular formula. And basically what it would tell us is in this particular compound, there are basically 2 carbons for every 4 hydrogens. That is essentially a 2-to-4 ratio of what is present between basically carbons and hydrogens. And if this is the molecular formula, the empirical formula can be found by looking at this formula and going, well, 2-to-4 is the same as a 1-to-2 ratio. Basically, if you divide everybody by 2, right, you get 1 and 2, which means we could actually reduce the molecular formula down to CH2. And this formula here would be what would be considered the empirical formula. It is the simplest ratio, whole number ratio of what is present in our molecular formula over here. So this is sort of the relationship between a molecular formula and an empirical formula. Now, in certain cases, the molecular formula and the empirical formula are exactly the same, like the case of water. If we look at water, which H2O is the molecular formula, that is basically 2 hydrogens for every 1 oxygen that's present, right? That is basically a 2-to-1 ratio. There is no way to reduce down a 2-to-1 ratio by dividing by a number and still get a whole number, right? If I divide by 2, I get 1.5, 0.5. Can't have like 0.5 of an oxygen atom, right? You got to have like a whole number sort of thing. So because there's really no way to reduce it down anymore, and that is sort of the furthest it could go, the molecular formula for water is also the empirical formula. So in some cases, both the molecular formula and the empirical formula will actually be sort of the same thing, because it is as simple and as far back as you can go. In certain cases, like the guy on the left there, you can reduce down the molecular formula to a simpler whole number ratio to get to the empirical formula like we did with CH2. All ionic compounds, as you may know, when we put an ionic compound together, we want to balance out the positives and the negatives together in the simplest way possible. And all ionic formulas are always empirical formulas. They're always the simplest way of getting to zero, basically. So empirical formulas, simplest whole number ratio, does not always mean it tells you exactly what's present, but it does tell you, again, the simplest ratio of what is present in that particular compound. If you're talking about the molecular formula, it tells you exactly what is present. So in the case of the guy on the left, it tells us exactly that there are 2 carbons and 4 hydrogens present in that compound. And just like water tells us 2 hydrogens, 1 oxygen. But again, the empirical formula is basically the simplest representation of that. Why is that important? Well, in most cases, if you're trying to maybe determine what the formula of a compound is, most of the time in the laboratory, people go for the empirical formula, because you can set up an experiment very much like the one we're going to do today or start today, where you can simply determine the empirical formula, sort of the simplest ratio of what's present. Any questions on the difference between those two? And again, we will obviously talk more about this on Tuesday as well. Now, another sort of important aspect of sort of empirical formulas, molecular formulas, is something that, kind of similar to what we did when we were calculating in experiment 6, say the percentage of water that's present. Basically, when we were calculating something like the percentage of water that was present, or even the percentage of the salt that was present in, say, that experiment 6, what we were doing was doing the percent composition by mass. And to calculate something like the percent composition by mass, basically you take the mass of what you're interested in and you divide it by the mass of the whole compound times 100%. So you could do that from formulas, again, very much like what we did with the hydrates. We just take water, for example, and we wanted to know what is the percentage of hydrogen by mass in water. The first thing that we would want to do is what we did today, which is get the molar mass of the entire thing based on the formula, which again, as we did earlier, 2 times 1.008 for our hydrogens, plus 1 times 16 for our oxygen, gives us a molar mass of 18.02 grams per mole. Now, since we're interested in the percentage of hydrogen that's present, there's 2 hydrogens that are present, which means that is the mass of hydrogen that would be present. So to figure that out, we would take 2 times 1.008 grams per mole. We would divide it by the mass of the entire compound or formula here, and we would times it by 100%. And if we did that, what that would tell us is 2 times 1.008 divided by 18.0, come here, 18.02 times 100% tells us that by mass, water is made up of about 11.19% hydrogen by mass. We could also do the same thing for oxygen. In this case, if we wanted the percentage of oxygen by mass, we would take the mass of oxygen that's present, which actually would just be 1 oxygen in this case. So basically 1 times 16 divided by the mass of the entire compound times 100%. And that would get us basically 16 divided by 18.02 times it by 100 gets us about 88.79%. Any questions on that there? Now, what that tells us is by mass, pretty much water is made up mostly of oxygen by mass, right? It's about 89%, and about 11% basically made up by mass of hydrogen. Now, because water only contains hydrogen and oxygen, we could have also at this point just took 100% minus 11.19% and sort of end up with our other percentage there. As I keep drawing lines all over the place there. We could end up with our percentage by subtracting it. When we add those percentages together, it comes out to, you know, around 100%. It should come out about 100%. Maybe a little bit different with rounding and stuff like that, but it should be in the kind of the 100% sort of ballpark. So a lot of times when we do sort of percent composition, our empirical formulas, molecular formulas, a lot of times we deal with percent composition by mass, and basically we just take the mass of whatever element we're dealing with, and we divide by the mass of the entire thing times it by 100. Any questions on that there? Okay. So in this particular experiment, our goal is to really sort of figure out sort of the empirical formula of silver chloride. You know, what is sort of the actual empirical formula there of our silver chloride. So to do this, we're going to do a couple of different reactions in this process that you're going to see. We're first going to start with really, again, trying to find the formula of silver chloride, which by the way is silver chloride, just so you know. All right, so we're going to start with actually solid silver. So in this case, we're going to start with some solid silver. And we're basically going to put some solid silver in an evaporating dish. An evaporating dish is just kind of a dish like this. And it's meant to, as it sounds like, be used to evaporate off basically liquid water or something like that. So we're going to take some silver, which is solid in this case. And we're going to take some nitric acid, HNO3. We're going to add it. So this is nitric acid. Nitric acid is a pretty strong acid, and it's going to actually react with the silver, and it's going to produce, you know, it has an option to produce a couple of different sort of things along the way. But it will produce some silver nitrate. We'll produce maybe some NO2 gas and maybe some water along the way there. And this process is done inside a fume hood. So this entire experiment, by the way, is done inside a fume hood. And the reason we do it inside a fume hood is because that is like a red, brown, toxic, deadly gas that is basically developed. So as you hit this, you obviously don't want to be smelling all that and inhaling all that. And they basically kind of put it in the fume hood. They put the evaporating dish in the fume hood, and everything's done in the fume hood. Nitric acid is added. They also put a watch glass. A watch glass is just like a glass circle on top of it to kind of cover it so it doesn't go all over the place. That's what's referred to as a watch glass. And basically this is going to obviously give off the NO2 gas and all that. But more importantly, this process that is being done here is really taking silver from the solid state that has actually no charge at this point to basically taking it to silver that actually has a charge at this point, which would be a +1 charge. So it's basically taken from 0 to +1 is basically what it's doing, as we'll talk about in a later chapter, oxidizing basically the silver from a solid state to a liquid state. And you may be wondering, why is it really important to do that? Well, it's important to do that because what we're starting with is the silver. We at some point need to add on there some chlorine or chloride to it. So we need to get the silver into really a form where it's able to accept basically the Cl coming in. In the form of solid silver, it can't really do that. It actually needs something with a positive charge because ultimately this is a metal, right? And this is a non-metal, which means we need our non-metal to be negatively charged. We need our metal to be positively charged so we can get that ionic bond to occur. And so this first process where we actually treat it with the nitric acid is the process where we basically oxidize the silver into basically a guy where it's able to basically sort of accept the chloride in, if you will, to make this solid. And what that really means is if you're sort of watching sort of what's happening, we'll just say with all the liquid and everything that's in there, there's liquid basically, right? And when we do this process, the silver starts out as a solid. It's basically not interacting at all. But once we add the nitric acid, it liberates the silver into silver ions that are now basically free floating around in the kind of the liquid part of the solution. So you're basically going to liberate the silver into silver plus, which is going to allow it to be what is referred to as being aqueous, part of a water environment basically floating around in a super zoomed of what's happening in the evaporated dish. So at this point, you're going to let it react, and it's going to react until all the silver is basically dissolved into, basically silver ions. There's definitely other things in there. It's not important. This is lost along the way out the top there, and as it's all sort of done. Now, once it's all reacted, we have our silver sort of in the right position to allow us to make basically silver chloride. So once we do that, we're actually then going to add to this another acid, and we're going to add to this hydrochloric acid. So once this is all done and all sort of reacted out, we're then going to take hydrochloric acid, which is another strong acid. So this is hydrochloric acid, another strong acid. And what it means when it's a strong acid is when we add something that is hydrochloric acid to a solution, it does not stay together. It basically breaks apart into H plus and Cl minus, 100%. So when we do this and we toss now in really into here, the evaporating dish, we toss the HCl into there, we're now basically adding to that solution a lot of H pluses, but we are adding a lot of Cl minuses, which are also aqueous and also floating around. And now what we've just done is we have silver ions there, we have chloride ions there. And as we'll talk about in a later chapter, those two guys have a very good attraction to each other. They want to come together and actually make a solid. And what's going to end up happening when we do that is basically the silver ion from the silver nitrate, which is this guy from here, will then react with the chloride ion from the HCl, and it will make a solid, which is silver chloride. Hence the actual formula of silver chloride right there. And that's going to make a white solid, and I'll just draw it as a blue solid here, but it will actually be more of a white solid here. And we're going to make this silver chloride solid. So that is sort of how we're getting both the silver and the chloride together in this reaction. It's basically two reactions. We're going to first basically react the silver by itself with the nitric acid. That's going to sort of prep the silver, if you will, into silver with a +1 charge, make it really a cation in that case. able to basically be floated around in the solution. Then second to that, we're basically going to add a strong acid, which basically, again, will react with the silver nitrate that's there, really the silver. And it will do a double displacement reaction, and it basically will make some silver chloride, and it'll make a little bit of some nitric acid sort of back as well. But the silver chloride making is more important here. That's really what we're looking for in this case. Any questions on sort of chemically, sort of what's happening here? So the question may be, how does this help us sort of get to, the actual formula for silver chloride? What we are left with at this point, I'm going to swap a page here. At this point, what we're left with after we have added the nitric acid, after we have added the hydrochloric acid, is we're now sitting with an evaporating dish that basically has some silver chloride solid in it. But it also has a lot of liquid component to it as well. It's got some nitrate ions that are floating around. It's got some hydrogen ions floating around. It's got some water in there floating around and stuff like that. And we're really interested in how much silver chloride we made. So the last part of the process here, after we sort of add those guys together, is we actually are going to put it up on a water bath. And we're going to put this evaporating dish on top of a water bath that is going to be heated. And as the steam from the heated water heats up the evaporating dish, that's then going to evaporate off, hopefully, all the sort of liquid part, if you will. And what we're going to do is going to continue this process until it looks like all of the liquid has gone away. And what we will be left with at that point is an evaporating dish that contains hopefully just the silver chloride solid, no more liquid. We're obviously going to weigh it, and then you're going to actually put it back up again, and you're going to heat it for a little bit. Going to heat again until we hit, like we've talked about before, constant mass. The idea of, again, heating, cooling till we hit constant mass is to make sure that we have clearly dried out our silver chloride solid, got rid of all the sort of water part, liquid part, and we have completely got rid of all of the kind of liquid part, and we're left with just a very dry silver chloride at the end. So that's sort of the process of this experiment. Reacted with nitric acid, allowed the silver to basically be available for the chloride that's going to be added with the hydrochloric acid. Once the silver ions and the chloride ions get near each other, based on solubility rules, they have a very good attraction to one another. They're going to come together, and they're actually going to make a solid. We then are going to evaporate off sort of the liquid component that's left over, because we're really interested in just the solid that's there. Any questions on sort of that overall procedure? Again, we go to constant mass to make sure that we hopefully completely basically got rid of all of that water and stuff. So how this helps us get to the empirical formula is if we just really look at sort of the experimental procedure and the evaporating dish, what was in the evaporating dish at the beginning and what's in the evaporating dish at the end, it will allow us really to calculate what we're looking for here, which is really the empirical formula. For silver chloride. So at the very beginning, and obviously there will be mass measurements made in the experiment, the very beginning, the only thing that we had in the evaporating dish was the silver. after we go through all of our processes of adding the HNO3, the nitric acid, adding the HCl, heating, weighing, cooling, all those things, at the very end of the experiment, when it's all said and done. And again, if you look at the table, say silver chloride after first heating, silver chloride after second heating, silver chloride after third heating, and so forth. Once we hit constant mass here at the very end, at the end of the experiment, what we have left in the evaporating dish is silver and the chloride together. So what we know is we started with a certain amount of grams of silver to begin with. We know that at the end, the only thing that was added to the silver is chloride. So if we basically find the mass of the chloride that was added by subtracting the evaporating dish at the end, which obviously has the silver chloride together, minus the evaporating dish at the beginning, which had just the silver together, that will give us the mass of the chloride that we basically added on to the silver. Any questions on that there? So at this point, when the experiment's over, you will know how many grams of silver you started with. You will know by taking the difference of what you ended up with in the evaporating dish to what you started with. That will give you the mass of the chloride. So how do we get this into our empirical formula? So as I talked about before, we're right there in terms of lecture, but just a preview of how you calculate the empirical formula. To calculate an empirical formula, you basically do a few steps, but the basic step is you take the grams and you convert them to moles. So in our case here, you will have the grams of silver you started with, which you then would want to convert into moles of silver. You also will have the grams of chloride that you had at the end from the calculation we just talked about, and you would want to convert it into moles of chloride, again, using the molar mass. Once we calculate the empirical formula, we convert grams to moles, then we divide by the smallest number of moles. So what does that mean? Let's just say, for example, here I got, let's just do, we'll do 10 moles of silver. These are not the right answers, 100%, just making these numbers up. And let's just say we did the conversion and we got 5 moles of chloride. What we would do is go, okay, between 10 moles and 5 moles, 5 moles is the smallest. So we would divide everybody by 5 moles. And that would give us a 2 for the silver. And it would give us obviously a 1 for the chloride. And that would tell us that my made up wrong molecular empirical formula here would be silver Ag2Cl. And this would be the empirical formula for our silver chloride. So again, you're going to take whichever one of these guys are the smallest and divide everybody by it. It obviously will turn one of them into a 1 and the other guy into a number. In this case, in most cases, in a textbook problem like we'll talk about on Tuesday, you usually just don't round. But here you can round to the nearest whole number. So for this experiment, and it's a little bit different for book problems, you typically don't round, but for here you can round to the nearest whole number. Should be okay. So usually an experimental sort of finding empirical formulas, it's a little bit okay to round. In textbook type problems, as we'll talk about on Tuesday, it's not necessarily okay to round in every situation, but here you can round to the nearest whole number, and that will give you, again, your empirical formula of your silver chloride. Any questions on that there, or this experiment as a whole? Obviously, you'll also be asked to calculate the percentage of silver in silver chloride theoretical. Again, the correct formula for silver chloride is AgCl. I guess we'll see how good they did in the video there. But this is the correct one that you would use for anything involving the theoretical sort of value. Any questions on that or this experiment here? And again, we will definitely hit empirical formulas, molecular formulas, percent composition there on Tuesday. It's kind of like almost where we kind of stopped lecture today. Any questions on that? So obviously this will not be due today or Tuesday or anything like that. So we're going to shoot for, we'll shoot for the end of next week. So this will be due next Thursday. That should give you enough time to sort of complete it. And obviously on Tuesday, we'll get the official lecturing on all these official topics here. So that would be 5, 6, 7, 8, 7, 8, I think, is when this one will be due. Again, it's going to be a typed report. It is a formal report. Again, you should be using your carbon pages, and pre-lab, post-lab, again, can be filled out on the actual manual pages and stuff like that. All right, so let's talk about a couple other things here. A reminder that we are also quizzing next week, right? So we are quizzing on Wednesday, I believe is the day I chose. So again, we're going to have a quiz on Wednesday of next week, which I guess would be 7/7, I believe. 5, 6, 7, yeah. And again, it will be on chapter 3 and 4. It's basically all about, you know, Lewis structures and all that stuff, geometry, hybridization. So basically everything that we covered up through yesterday in terms of bonding is fair game. Kind of probably very similar to study assignment B. Very similar to that one. It's probably, you know, kind of like what the quiz might entail and stuff like that. Again, we will do that, I think, probably, like I said, at the beginning of lab on Wednesday. So we'll lecture like normal and then do a little bit of lab. Monday is a holiday for the 4th of July, right? So there's no class on Monday. So we will then see each other again on Tuesday after today. So we have just Tuesday, Wednesday, and Thursday of next week. I think in terms of what is due or what's out there at this point, I think it is just study assignment B. I saw some of you look like you turned it in already. But again, that is due today, which is obviously the bonding and all that kind of stuff. Any questions on what's going on here? Okay, other than that, I really have nothing more, I don't think, to say.